I mean, you can do it a couple of ways. If you look at this, it makes logical sense to just, well, I said that. If I assign a charge to the top and bottom, y'all follow me on this? If I just say I'm going to put a charge, I don't know how Winkler's book does this, because typically with a parallel plate, they put a voltage difference. And then, did he do it that way, or did he assign a charge?
I think he assigned a charge.
Either way he'll do it. I'm just kind of curious, because if you assume a voltage difference, then you solve the del squared equation.
He assigned a charge.
All right, so you're going to assume that there's Q here and then minus Q on the upper plate. And either way will work. We could do the del squared equation, it will work. So if you do that, all right, now you get a surface charge density, rho s, and that's going to be equal to Q over the area. And you can put a magnitude here and a magnitude here. There'll be a positive to negative charge density. Did you all agree with that, class? Now, you know you got a perfect conducting plate here, right? And a perfect conducting plate here. What does rho s give you? D normal, doesn't it? So what we've done is going from charge, assume charge, then we get rho s is equal to Q over the area. Then we get D normal is equal to rho s. And in this case, it's a little tricky because these are plates. So there's a D field above and below, but the D field, actually, there's only going to be an electric field in this region between the plates. And frankly, at this one, if you just had a very thin plate where you had rho s on it, the D field in either direction would be the same magnitude, and the magnitude would be rho s over 2, because it's literally, it's not just a perfect conducting plane where it's only going one way. Does this make sense to everybody? Now, the D field in here will be this value. So this will be rho s, and I should say inside capacitor. Now, once you have the D field, D normal, equal rho s, you also know the D field is the E field, right, times epsilon, correct, class? Therefore, you can get the E field and say it's equal to rho s, and I'm just going to leave it as rho s for this part, over epsilon naught epsilon r. And that's epsilon r there, which is 3 times 1 plus z. And it would be in the AZ direction. Now, we know rho s is Q over A, but Q is an assumed value. We're just going to leave it like that, okay? Now, after you get E, the next thing you got to get is what? V, correct? You got to get the voltage difference between the plates. I'll warn you about one thing with these things. You can get real casual and make mistakes here, especially with these integrations if it's in cylindrical or spherical coordinates. Just be aware of what's going on. So for V between the plates, I'm going to integrate from 0 to the height h of the plates, or thickness. It's 1 centimeter, but I'm just going to list this as h here. And if I do that, then I have rho s over 3 epsilon naught 1 plus z, and this is az, and it's going to be dot with the differential length, which is dz az. Now y'all follow the train here. I assume Q, got D, from D get E, from E I need the voltage. Do y'all follow me? When I do this, I get rho s over 3 epsilon naught. The AZs are going to dot out to 1, and then I get the integral of 1 over 1 plus z dz from 0 to h. Probably the easiest way to do this is make a variable change. Maybe there is an easier way. But if I let u be equal to 1 plus z, then du is simply equal to dz. So I can say this is rho s over 2 epsilon naught. That would be the integral, let's see, if z starts at 0, this would be from 1, and it would go to 1 plus H. And then it would be 1 over U du, and that's a natural log, so this is going to be rho s over, 3 epsilon, not 2 epsilon. 3 epsilon naught times the natural log of 1 plus H over H. And that would be V, and then I'll put the values in over here. And therefore, we know that charge is equal to Q, or charge Q is equal to CV, or C is equal to charge over V. I assume the charge right there, so it's Q, and then it's divided by that voltage. And rho s is Q over the area. So this is Q over the area. I'm looking at that. And then it's divided by 3 epsilon naught, which brings 3 epsilon naught here. And then it's divided by the natural log of 1 plus H over H. The Q's got to cancel, so I have 3 epsilon naught A over the natural log of 1 plus H over H. I don't know if you did it that way quite the same way, more or less. When you plug in the values, you got to make sure you get the units right. That's 50 centimeters squared. So if the units of capacitance are going to be in farads, you're going to have to change this to be equal to 50 times 10 to the minus 4th meters squared. Y'all follow me on this? Because that's centimeters. Centimeters is 10 to the minus 2 meters. If you square it, you get 10 to the minus 4. And you'd also have to make sure H is, that's 1 centimeter, which is 10 to the minus 2 meters, and you would do that problem that way. Agreed, class?
Yeah.
Does that give you the right answer?
It does.
Pardon?
It does.
All right. One of the things you're going to have, you always face this fact, is when you're doing a problem like this, and you're unsure to assume voltage or charge, the normal way I do it, if it's a planar case, I usually assume voltage for planar cases, usually. However, for this particular problem, it'll be easier to assume charge and go backwards. I'm just telling you that. This is one of these exceptions. Now, any other cylindrical or spherical case, I assume charge right off the bat. Charge on a plate, and I go through it. If the actual layers are concentric, if they're, they're surrounding something. But if they're in parallel with each other, then I would assume voltage. And I don't want to spend too much time on that right now. All right, you get the hang of this, the more problems you do. I'll probably give you a few more problems related to this. Y'all follow me on this one? Any other questions? Now today, before your quiz, unless there's something related to the quiz you want to ask me, what I want to do is cover a few more things in magnetostatics, specifically the application of the Biot-Savart law to an infinitely long, or just a long straight line of current, and also a ring of current, and you get your quiz. By the way, how many are staying here for the game?
I'll be here.
Nobody. Well, I am. I want to see this. I thought there was going to be a parking lot filled with tailgaters and stuff when I was here, but I guess that's fake news. All right, so next thing is this. We know when we have an actual current I dl, and that's a vector, and you have a radius vector r, and you want the dh from this, that's equal to I dl crossed into ar, a unit vector pointing from the source of the current, or pointing from the current source to the position you're actually observing the H field over 4 pi r squared. That's it, in a nutshell. Very similar what you saw dE was from an actual chunk of charge, which is just dq over 4 pi r squared ar. Very simple. It's inversely proportional to r squared. It's weighted by the magnitude, like this is a charge that's weighted by the magnitude of the current times dl. and it's crossed into AR here, which is the difference. So now an application of this to an infinite line. If you look at this, I mean, this is a classic problem. So you probably did this in physics, whether you remember it or not, another story, but it's a classic. If you have the z-axis here, you have a current I that doesn't vary on the z-axis, and I come out a distance rho away. Now the book here assumes it's infinite, but it doesn't have to be infinite. It can be semi-infinite, or it can be from any position A to B. And I want to know what this differential H is right here. What I need to do is identify a portion of the source. So you just take a little chunk of current that's at a height Z, so the altitude of this thing is Z, and there's a radial distance R out, and this is going to be my R vector. Y'all follow me on that? Now R, it's important you get this one right. This is a vector. It always goes from the actual current source, this is the differential current source, IBL right here, to the observation point. And I'm just saying it's out a distance rho. Y'all with me? This has to be 90 degrees. So I say it's going to be I, that's constant value, and it's times DL. Well, DL, we're in the Z direction, so it's DZAZ. Does everybody follow me on that? When I'm talking about differential length, it's a vector. You have to have a differential, dx, dy, dz, something like that, and it has to have a vector direction or sense. It's in the Z direction. So it's IBL over 4 pi r squared, where r in this one is what? I'm asking this for a reason. Force yourself to ask yourself the question, what is r? If this is the point, the source point, what is this vector r? Remember, it's the positions here minus the positions here, correct, class? So if you do this as a cylindrical coordinates, when I take rho at this point, it is rho. What is rho at this point? 0. So it's rho, a rho, right? Now what about z? Well, the z at this point, you might as well put it at 0. Y'all follow me on this, class? Make your life easy. If this is 0, right, then this is z. Y'all follow me? So it would be minus ZAZ. Now please see, the way it's pointing downward kind of tells you that the z has to have a negative component, the rho has to have a positive. Y'all follow? You get down to that for r. So I'm going to take this, that means magnitude of r is really equal to rho squared plus z squared to the 1/2. If I square it, I get rho squared plus z squared here. That would be the r squared. And then this is crossed into AR. How do I get AR, class? You remember? If I have a vector r and I want a unit vector, what do? I take the vector divided by the magnitude of the vector, which would be the square root of rho squared plus z squared. So this becomes simply rho, a rho, minus ZAZ, and since it's over this, I just make this to the 3/2 power. This should look eerily familiar to the way we did it with the infinite line charge. Y'all with me? Now, something you always take a careful look at, and don't just brute force anything, is can you simplify stuff? So here's a question for everybody. Don't answer out loud, just think. What is AZ crossed AZ? Think about it. How many think it's 0? It is. AZ crossed AZ is 0. AZ dot AZ is 1. This is a cross product, not a dot product. Y'all with me on this, guys? So that means this portion of the integration goes away. I will see people do that portion of the integration if I don't really beat this in. Y'all follow me? AZ crossed AZ is 0. AX crossed AX is 0. AY crossed AY is 0. In general, any vector crossed into itself is 0. If it's dotted into itself and it's a unit vector, it's 1. Now, what is AZ crossed A rho? You got a right hand, right? Let's hope so. Anyway, AZ up, right? A rho out. Thumb is in the A phi direction, isn't it, class? Let's try this. If this is the Z direction, and this is the rho direction, Now we know we could superimpose something. We could say that's X, that's Y, correct? All right, just take a look at this. AZ crossed A rho. You with me on this? Where's your thumb point? Into the board. Should, right? Your thumb is the hinge. It should point on your right hand into the board. Well, what is going into the board? Isn't that the A phi direction? Can you all see that? And this will take a little time. You've got to do this, you got to work with it, but you have to make certain you understand it, because if you don't, you really will start doing dumb things on quizzes and exams. So make sure you work through the problems I give you related to this stuff. That means I can take AZ cross A rho and just replace that by A phi, correct class? So I had what? Up here I had rho A phi, correct? Because I had AZ crossed A rho, correct? And there was a rho in front. You all with me? Now, that's just DH, but I have to integrate this thing. This is the one, I don't hold people's feet to the fire on this type of an integral. I would give you a table for this thing. Now, I need to integrate this to get the H field. And in general, I'm going to integrate from the lower to the upper. Here, really, the lower limit is going to tend to be minus infinity. The upper limit is infinity. When we do this, what I do is see what I can take out in front always. I got I as a scalar. Rho does not change. It's a dz integration. 4 pi doesn't change. So I have I rho, and I can take a phi out in front too, over 4 pi. And then I have this integral. Integral of dz over rho squared plus z squared to the 3/2 power. And this is going to go from minus infinity to infinity, or from the upper to the lower. Now that integral you can do, that's a trig substitution. I think it's a sinc, or a sinc x thing. Anyway, this one will end up being, I'm not going to mess around with that right now, and it will be over 4 pi. And then you're going to have z over rho squared plus, or rho squared times the square root of rho squared plus z squared. And here z is going to go from minus infinity to infinity. You all follow me on that? That's just the, if we wanted to do that integral, I don't worry about these things. I used to. We could do it. And you've had calculus, so if push comes to shove, you can refresh your memory. And these days, you just look it up on Wolfram Alpha or one of them things. These things are fairly well known, but it's a well-known integration. Now what happens, just take a look at this for a second. What happens to this when you let z go to infinity? All right, I want you to take a look at this. When it goes to infinity, I got infinity, then I got the square root of infinity squared, where I got infinity over infinity, or 1. Then minus, then z goes to minus infinity, so it's minus infinity over infinity, or minus a minus 1 is going to be 2, right? I mean, it's going to be plus 1, 1 plus 1 is 2. This whole thing will come down to be, and this is the one thing you take from it, for an infinite line, if you're out a distance rho, the actual H field in the phi direction with respect to this axis will be equal to I over 2 pi rho in the A phi direction. Now, doesn't that look remarkably similar to the E field from an infinite line charge? Do you all remember that? I want to just contrast those two so you will have that in your memory. All right, that's for an infinite line charge. I mean, that's for an infinite line current. If you had an infinite line charge on the z-axis, and you're out a distance rho, do you remember the E field was simply equal to rho L over 2 pi epsilon naught rho, or really epsilon, A rho? Do you remember that? How many do? This is one of those things you should be able to, in your brain, store this and say they're so similar. Only this electric field points away from the source, or from this has an H field that swirls around it. If you look at the actual field lines, they do this. They basically are swirling around that way. That's an important distinction. Are you with me? Now the next one that's classic and we have to do is going to be a loop. We've done a loop with charge. Now we do a loop with current. And this is the beginnings of, once I get this, I use that as the building block to get the actual H field from a solenoid in the center of the solenoid. And believe it or not, you guys ever look on YouTube to see some of these nutty things kids make or students make? Well, one of the things they make is called a coil gun. Has anybody in here ever heard of a coil gun? Anybody here heard of a rail gun? All right, well, a rail gun is something that has two rails with a whole lot of current that generates a magnetic field. A coil gun, but the rails have to be in contact with the projectile. A coil gun has, and I've built this one too, tons of coils, and when energized, you put a ferrite rod material and you will suck it in towards the center. And before it gets there, you quench the H field and it comes flying out. Coil guns, I learned the hard way. I mean, it was a kind of a shock, are absolutely silent. They are an assassin's best friend in a sense because there's no sound, and I mean none, unless you break the sound barrier. We built them, I did this for a project for a grad student over in fiber and polymer engineering is trying to propel, if you know anything about weaving, they have a shuttle that holds stuff and flies in and out of fabric as it goes up and down. It's a shuttlecock thing. Anyway, well, he wanted to replace that with something that shot through and then shot back, pulling a string. Interesting idea. First, we had to build the thing to do it. There's a coil gun we want to use. I said, all right, I'll help you build it. Right? I'll make sure you don't kill yourself. That doesn't sound like a very promising idea. So we built it upstairs. I'm not kidding about this. And I thought, you know, maybe it'll come out and hit the ground like that. We didn't go through deep calculations. We used basically some of the equipment on these, remember the old, you'd buy these cheap little cameras that had flash bulbs, and they have a step-up transformer off some capacitors. So he basically did that with an order of magnitude, used the same stuff that actually triggers the cameras. Same exact, more or less switching. And we had maybe an order of magnitude more energy on the capacitor bank. And he used just a nail. I mean, just a nail. And you stick it in this tube, plastic tube, sort of like a big pen with wrappings, all these coils. Fires it. I don't hear anything fire. The only thing I hear is something hit the wall, and it sounded like a bullet. And bam! And I looked. And that thing did that. And that's when all of a sudden we had a whole new set of rules for how we're going to do this test and stuff. Because it's a bit shocking. On YouTube, they've got coil guns, kids make, they got rail guns. I started looking at this stuff. I'm like, you let this stuff up? Somebody's going to put two and two together, there's going to be a lot of trouble. These things can be scaled up to be really problems. I know some people say, why not just buy a 45? Oh, that's a good point, but they're loud. This thing ain't. That's my little story. It's an application of something dealing with not one coil, but many coils. So here's the first coil you have to learn about to get there. Make a note to yourself, go look this up and you'll get a kick out of it. So I'm going to have a loop like this, and it's going to have a radius A, and it's going to have a current I, and it's going around circle. It's, you know, this is in the XY plane, and I want to know what the H field is on the Z axis. That's my goal. Can you all imagine the problem? Just got a loop of wire that's got a current, and I want to find what the H field is on the Z axis. So what I do is this. I say this distance is going to be Z above, and I'm going to take a differential chunk of current out here, and I'll just call that IDL. And this is my radius vector R. I hope you can see this. So when I'm doing that, What I really need to do is get the DH, right? I need to find the differential H field up there at this point. And again, the general form is DH is equal to I dl over 4 pi r squared, and it's going to be crossed into AR. Usually what we do, and write this down because you should do this, this is normally given as I dl crossed into R vector over 4 pi magnitude of R cubed. Now the reason I did that, you don't have to worry about calculating a unit vector. If you have R vector, it's inherent to that statement of the problem, all right, to the differential. So now you have to define which each one of these are. R vector goes from here to here, right? So what would R vector be? Start with the radial. Do you all agree cylindrical coordinates makes sense to be used here? All right, when I'm doing this, that has a radial distance of A. The point of observation has a radial distance of 0, so it would be minus A rho, right? So R would be minus A rho. And what about Z? It said 0 here, and it's at height Z here, so it'd be plus ZAZ. You all agree with that? Now, because we're right on the z-axis, A phi loses its meaning. Don't even worry about A phi. And I'm going to make an argument of symmetry to get rid of that problem integral in a second. So I have this, and now I put this together for DH. And I see that DH is equal to IDL is what? I didn't put it down here. What would that be? Well, you've got to give me this. It's got to have an I, right? In front. What is DL is what I'm getting at. Think about this. Remember the wiper arm length from the center? If it moves a certain distance, what is that? This would be D phi, right? And it would be A D phi would be the wiper arm tip length, right? So it would be A D phi, and it would be in the A phi direction, right? Right? A phi is the direction the current is. Do y'all follow me in this class? That's crossed into R, and R in this case is minus A rho plus ZAZ over 4 pi, and then it's R cubed. Well, if this is R, the magnitude of R would just be equal to A squared plus Z squared to the 1/2 power. And if I cubed it, I get A squared plus Z squared to the 3/2 power. You all agree with that? I'm trying to make my case as simply as I can. Agree? Okay. Let's do this cross product business. Use your right hand, and don't worry if you don't get it. You will. If I have A phi crossed into A rho, now think about that. Phi, right? Well, we use the board here. So if I'm going in there, phi crossed rho would be minus AZ. Y'all see that? You might not. Look at that, honestly. It takes some time to get used to it. You're used to X, Y, and Z. The phi thing always throws you because phi points in a different direction, A phi points in a different direction depending on the value of phi. Right? Yeah. You just think about that. All right. So this one, it's going to be, it's got to be Z. As a matter of fact, these two are orthogonal. The only thing you can get is Z. It's minus Z, but there's a minus there, right? So that makes this positive AZ. Follow me? So I'll get rid of this. I'll put positive AZ for this portion. Now, when I get A phi crossed AZ, what is it? A phi crossed AZ is A rho, isn't it? Y'all with me? A rho. So I'm going to get rid of that. Now, that's dH. And to get h, what do you think I'm going to do? Integrate it, right? No? No. I'm going to go ahead and integrate it, right? Where do I integrate? Well, my integration is d phi. Where do you go if you're integrating d phi around a circle? You start at 0 and you go how far? To 2 pi, right? From 0 to 2 pi. So phi goes from 0 to 2 pi. You're right. But I have a statement here. I'm going to just make this statement. You see how it has a rho here? Now, technically, I'm not going to spend a lot of time on this. A rho is actually equal to cosine of phi ax plus sine of phi ay. Promise you it is. And if I replace a rho here with that, just listen to me. What happens when I integrate cosine of phi or sine phi from 0 to 2 pi? It's always 0, right? If you integrate either sine or cosine over an entire period, you always get the same amount of area above the curve as below. It goes to 0. Y'all hear me? It means this will cancel mathematically. What Wentworth does is make arguments of symmetry. He says for any little chunk of current here, there's a chunk of current on the opposite side, 180 degrees away in phi, that will have the same differential h field in the z direction, but the rho components are canceled. That's his argument. It's called an argument of symmetry. Y'all with me? This is a mathematical argument that's rigorous. It'll still get you the same result. It's 0. So I just get rid of this part. Never make your life more complicated than it needs to be. Now I do that integral, and this is the nice thing about this integral. When you do it, take one look. The integration is with respect to phi, right? Does anything else inside that kernel of integration depend on phi? No, right? When I integrate d phi, I get phi, right? I mean, if it was like d phi sine phi or something, then it would, but it doesn't. So when I do the integration, the only thing I end up getting is multiplying this by 2 pi, or when I multiply that by 2 pi, it's just getting rid of one of those 4 pi's and putting a 2 there, and that, in fact, is the h field on the z-axis. Get rid of that, and you're going to see there's an a squared here, which is interesting. So that is actually the value that's in the a z direction of the h field. It's a squared over 2, a squared plus z squared to the 3/2 on the z-axis from a single loop. I have a question for you. This is just something to see if you're thinking. If that's what it is for one loop, what happens if I put 2 loops on top of each other? In other words, if I have some wire and I wind one wire right on top of the other, but they're shellac or insulated, what do you think is going to happen to that H field? It would double. 3. Triple. As a matter of fact, if they're tightly wound, the more windings just do one thing. They effectively increase the current, right? Flowing, that's the only thing they do. That's basically the thing with a solenoid. Y'all know what a solenoid is? It's just a whole lot of wrappings or of turns on some sleeve, cylindrical sleeve. Solenoids can get you a lot of H field in the center core based on it. Now, something else I'm going to say, and this is important to see. Remember how when we had a loop of charge, we have a ring of charge, and we're on the z-axis, and this is rho L, that the electric field right at the center is 0, isn't it? Right at the origin. If this thing's in the xy plane, it is 0 because the differential amounts of charge all cancel the electric fields from all cancel each other out. What's the H field right here at z equals 0? Take a look. What is H for z equals 0? All right, do the math on this one. Z equals 0 is not hard, right? Just get rid of it. Now I have a squared over the quantity, a squared to the 3/2, that's a cubed, isn't it? Right? So I have a squared over a cubed, or 1 over a. Don't I, class? So I really have I, right, over 2A AZ. It isn't zero. There's something else that happens. What happens if I take Z and I make it negative? Does the direction of the H field change? Take a look. Look at the equation. This is a square, by the way. No, it doesn't change. And this is the interesting thing. Unlike when you have a loop of charge, the E field down here is in the opposite direction for the E field here, and it has a relative zero there. Here, the H field is always going to be in this direction, which is good for some engineering things we do with this stuff, like coil guns and rail guns and stuff. But it really, coil guns, but it frankly is always in the same direction. What happens as Z goes to infinity to the H field? Last comment. Just look at the equation. Make Z go to infinity. What happens to the value of the H field? Zero, and it has to go there. If anytime you have an infinite distance from a finite amount of current or charge, the value of the field quantities, D, H, E, whatever, have to go to zero. Do you follow me on that? That's a simple check, a mental check. All right, I had to get through those. And I'm going to say that I'll give you some more homework. We'll talk about Ampere's law next time. And now what you've been waiting for your whole life.